qualitative thing with retrograde motion, but it even has a novel, or not novel, but a novel, it explains something it wasn't designed to explain, which means that this has amazing predictive power. It not only explains retrograde motion, but explains why planets are closer during retrograde motion. This is a beautiful, beautiful thing. And this created much, much more precise. The larger circle is called a deferent, the smaller circle is an epicycle. The one deferent, one epicycle system was much more precise than a system with just circles. It allowed for fantastic levels of prediction, comparatively. And it made the correct qualitative predictions as well. So clearly this is correct in some sense in the ancient world. It is obvious that this must be right. The problem is that it's still not perfect. The fact that things don't stay at the ecliptic is still not explained. Because, right, this would still be expected to be on the same plane. And the times between retrograde motions are not exactly the same, which they should be, because this is rotating at a constant speed. But at the same time, this is an amazingly promising beginning. We need to fix it. But we've got our start. We've got something that's obviously mostly right. So, the rest of ancient astronomy, and up until Copernicus, well, even Copernicus himself, was essentially engaged with honing this model so that it made the exactly right predictions. Because we've got the right qualitative predictions, and we've got pretty good quantitative predictions. Now we just need to get perfect quantitative predictions. So we just need to mess with this model until it's perfect. And there were a few things that they used to do this. First of all, epicycles can even help the sun. Because while I was saying that the sun was explained, that's a little bit of a simplification. The sun does move around the ecliptic, but it does so in a way that's not perfectly consistent. The time that it takes it takes 6 more days to move from the vernal equinox to the autumnal equinox. And essentially it moves faster during the winter. This is a problem if it's on a circle moving at a constant speed. But a very minor epicycle can explain this. Because if the epicycle is rotating, such that one rotation takes the same amount of time as the deferent takes to rotate, you don't get any retrograde motion. Instead, you simply get, and you don't get any complicated patterns of faster and slower, but you do get a simple pattern of faster and slower. And that half the time it is going faster than you expect, and half the time it is going slower than you would expect. So this epicycle system is now even explaining the difficulties with the sun. And there are other, specifically, if the radius of the epicycle is 0.03 times the radius of the deferent, you get exactly the right 6 days difference. And there were other tools. Sometimes they put an epicycle on an epicycle. You can get even more detailed things this way, more detailed motions. You can explain the fact that the difference between retrograde motions is not quite right, because this epicycle will be subtly changing the overall pattern, so that the time between retrograde motions will be faster or slower as needed. And you figure out the right values, and you get an even more accurate prediction. There are these things called eccentrics. The idea of an eccentric was, yes, it's rotating around the Earth, but the center of the circle is not the same place as the Earth. This is still a perfect circle. It kind of fits the whole, ecliptic is not at the center of the star map. There's nothing intuitively wrong with this. Clockwork, the universe can still move like clockwork, and the clockwork be a little bit offset. And this can be used to get some of the same features as epicycles. You can eliminate some epicycles by doing this instead. Because, right, it would seem that if it's moving along this circle at an equal amount of time, then it will seem to be going faster as it's closer, and it will seem to be going slower as it's further. So this can explain some of the same things that epicycles can. And a combination of eccentrics and epicycles can do even better, obviously. There's a thing called an equant, which is particularly important. And it's particularly important because Copernicus hated it. He thought that it was a perversion of astronomy. And a large part of his motivation was to get back to this simple system and get rid of this terrible new invention, the equant. The equant says that it's centered around the Earth. Or it doesn't have to be. It can be an eccentric and an equant at the same time. Well, let's say it's centered around the Earth. But its rotation is measured against a different point. So that the angular distance, essentially, is moving at the same speed. So that things move slower over here than they do over here. It's also interesting because this is very similar to a system Kepler ended up introducing, which was the first major break from Ptolemaic astronomy. But Copernicus hated it. He thought it was the worst thing ever, and he was largely attempting to get away from it. Now, combining all of these tools in their various permutations and with various values for each of the speeds of rotation and the radius of the circles, that was essentially the driving force behind astronomy for the next 1,500 years. Because we've got the basic system clearly, and now we need to make it perfect. And we've got these tools for figuring out exactly how it fits together. Aristotle was, this is the technical side of things. But equally important is the kind of interpretation, the way people looked at it. And Aristotle was incredibly influential with this. He took this idea of homocentric spheres, which Eudoxus created, and said the universe was filled with 55 of them. This is exactly 55. The spheres are made of something called ether, which is the fifth element. In his writings, it was a crystalline solid, although many people after him disputed the fact that it may not actually be solid. It was the lightest element and the most perfect. The reason there are 55, there only needed to be about 25 to explain the motions of the planets. But the 55 was so that it could be set up to work like clockwork, such that he believed that the nature abhorred a vacuum. And so the entire universe was filled with something. And from the edge of what we would now call the atmosphere to the stars was completely filled with ether in the form of these 55 spheres. And the movement of the stars drove the movement of everything below it. So the stars pushed on the next sphere, which pushed on the next sphere, which pushed on the next sphere. And they did so in this precise way that he worked out. I don't know exactly how good it was, but he worked it out and he thought it was good. And the innermost ether sphere caused all movement on the Earth, because the four less pure elements, air, water, earth, and fire, could be mixed up in a way that the ether couldn't. And as the innermost sphere moves, it pushes on the air near the edge, which pushes on everything else. And that's why we get movement in the earthly realm. And there were, and the laws of motion were explained this way too. Things want to go to their natural place. Specifically, lighter things want to go up, and heavier things want to go down, where down is defined as the center of the universe. So Earth is at the center of the universe, exactly like it is. I mean, the Earth is at the center of the universe. The ether, being the lightest element, is far away, near the edge. It takes up most of the space, but that's because there's a lot more ether than there is anything else. The other three are in the middle. Water being slightly heavier than air, but lighter than earth, and fire being the lightest of the four, and then the ether being lighter than any of them. And these laws of motion were essentially accepted for a long time. So this whole system, while admittedly not entirely commensurate with the idea of epicycles, it's hard to get epicycles to make any physical sense in this system. At the same time, this was how it was thought about. This was the popular interpretation. This was the way that, this was a very important conceptual scheme, even if it doesn't quite fit with the technical side of things. But it's very similar to the technical side of things. You still got spheres, you still got circles. Getting Aristotle to early modern Europe was a difficult event. It went through Syriac translators and Arab translators and all sorts of things. It's a very long and very interesting history that I'm not really going to go into in the interest of time and into the interest of me not knowing that much about it. But there's an excellent book about it called Science and Translation by Scott L. Montgomery, if you want to read that. I've read it, it's a great book. But it did eventually get back to Europe.